Hi everyone, hopefully everybody is fine. Today we are going to continue with chapter 3, current flow in homogeneous semiconductor. Our focus for today is minority carrier lifetime and quasi-Fermi level. In the previous subtopic, we have discussed on the generation and recombination where electrons can be generated by thermal or optical energies from the valence band to the conduction band, and then electrons will recombine from the conduction band to the holes in the valence band. We will further discuss in this subtopic on the duration and length of the electrons being at the conduction band before they recombine. The learning objective of this topic is to understand the concepts of carrier lifetime and diffusion length, and also the concept of quasi-Fermi level. Carrier lifetime is defined as the average time that electron spends in conduction band before it recombines to the valence band. Or we can say that it is the average time taken from the generation process to the recombination process. In order to study the carrier lifetime, it is easier to observe the optically generated carriers, which means we can measure the increase of current through a sample in the presence of light. For example, we can easily monitor the increase of current through a p-type semiconductor under light. The increase of current in the p-type semiconductor is due to the excess electrons generated when the light is on. Thus, we are actually monitoring the minority carriers. So, the method to measure the carrier lifetime is as shown in the figure. We have a sample, a thin sample and a uniform semiconductor which is connected as shown in the figure. Then, the optical pulse is applied onto the sample. An optical pulse is turning the light on and off for some fixed duration with a number of repetitions. When the light is on, electron and hole pair is created through absorption. That means there is an increase in current, which is measured by the oscilloscope as the time variation of voltage across the load resistance RL. The results may look like this figure if the carrier concentration is plotted versus time. When the light is on, there is an exponential increase in the carrier concentration until it is saturated, and the carrier concentration will decrease when the light is off. The time constant is denoted by tau, and an example of experimental data of the carrier lifetime is shown here. This plot will be used to determine the carrier lifetime of a specific material with given doping concentration. We can see that when the doping concentration is high, the carrier lifetime is shorter. Besides carrier lifetime, we also need to know the carrier diffusion length. In a simple word, how far can the carrier travel? For electrons, how far can the electron travel in the conduction band, and for holes, how far they can travel in the valence band. The method to measure is to apply light source on one end of a semiconductor and measure the current with regards to position. Theoretically, as the electron travels or diffuses along the conduction band of the semiconductor, they will tend to relax to the valence band and thus reduce the current. This figure is an example of a plotted carrier diffusion length as a function of doping concentrations. We can find the carrier diffusion length for silicon from this figure, or the diffusion length also is given by this equation, Ln equal to square root of dn tau n. We can also observe that with increase of carrier concentration, the diffusion length decreases. We have learned that once carriers are generated, for example by light, they will be at the conduction band for some time and travel for some distance before recombination happens. When we apply a light source to a material, for example in this case a p-type material, excess carriers delta n and delta p are produced. Thus, at the illuminated end, the total carrier concentration becomes n equal to n naught plus delta n and p equals to p naught plus delta p. In this case, the generated electrons delta n is high. and at the same time, an equal number of holes, delta P, are also generated. Thus, this will result in a split of Fermi level, and this is what we call quasi-Fermi level, as shown in this figure. This happens because there are high number of electron concentration, and at the same time, there are also high number of holes concentration. Thus, the Fermi level will split, becoming EFN and EFP. EFN is the quasi-Fermi level for electrons, and EFP is the quasi-Fermi level for holes. Notice at the dark end, the carrier concentration is the equilibrium carrier concentrations without the delta N and delta P. In this example, since the sample is a p-type semiconductor, P0 is equal to Na, and thus N0 is Ni squared over P0. We have learned that the carrier concentrations under equilibrium is given in these equations. Under non-equilibrium condition, these equations can be modified to the below equations. Bear in mind, N is N0 plus delta N and P is P0 plus delta P. And the EFN and EFP are the quasi-Fermi levels, as what I have explained in the previous slide. Solving these equations, we have the equations for EFN and EFP here. Note that using these equations, we assume that the semiconductor is a non-degenerate semiconductor and the excess carriers generated is not too high that it maintains the non-degeneracy of the material. With the quasi-Fermi level, the current densities for electrons and holes can be calculated using these equations. To summarize this subtopic, we have learned about the carrier lifetime and diffusion length. The carrier lifetime is the average time of the generated electron spans in the conduction band before recombination happens. On the other hand, diffusion length is the average distance of a generated electron diffuses before it recombines. And we have also learned about the quasi-Fermi level in a non-equilibrium semiconductor. That's all for this subtopic. We have covered all chapter 3, and if you have any equations, please ask at the comment section in the related post in our FB group, or you can ask me through the WhatsApp. Thank you.